particles play a fundamental role in shaping our understanding on cosmology, as they provide key insights into the formation and evolution of the universe. From the earliest moments following the Big Bang, the interactions of elementary particles, including photons, neutrinos, quarks, set the stage of the cosmic structure we observe today. The study of these particles allow us to explore crucial phenomena such as dark matter, dark energy, and the origin of the universe. Now, to talk more on this today, we are honored to have a distinguished guest, Dr. Nilanjana Kumar, with us. Dr. Kumar has an incredible academic journey, holding a PhD from the Northern Illinois University, USA. She has been a postdoctoral fellow at SINP, Saha Institute of Nuclear Physics, Kolkata, as well as a DS Kothari postdoctoral fellow at the University of Delhi. She is making remarkable contributions at the Thanu Padmanabhan Center of Cosmology and Science Popularization at SGT University, Gurgaon. We are thrilled to have her share her insights on the profound connections between cosmology and particle physics. So, wishing Dr. Nilanjana Merry Christmas and a Happy New Year, as well as to all the viewers, Merry Christmas and Happy New Year. Let us welcome Dr. Nilanjana.
Thank you, Shaunak. Thank you for this nice introduction. This is my first podcast, so Merry Christmas and Happy New Year to you and your family as well, and to all the listeners and viewers. So, yeah, I come from the Thanu Padmanabhan Center for Cosmology and Science Popularization. So, this is in SGT University, which is in Gurgaon. So let me just share my slide. I just want to show you this slide. So this is our university, which is in Gurgaon, and this building here on the right, this is our center, the Thanu Padmanabhan Center for Cosmology and Science Popularization. And currently we are 5 faculty members, including our director, Professor Sami. And these are our current PhD students and project students who are working with us and publishing papers. So we currently have a PhD program running with specialization in high energy physics, astrophysics, and cosmology. So if anyone is interested, you can contact us, or you can contact me or Shaunak. And also you can come and visit us. We will be glad to have you at our center. And we do science popularization activities as well. So yeah.
Absolutely. Thank you, Dr. Nilanjana. And just to let all the viewers know, this is the wonderful University of Gurgaon. As you already know that first I had a podcast with Professor Shantan Chaudhary. I think he is now at the Warsaw University in theoretical physics from the same SGT University. So thank you, Dr. Nilanjana. Can I put the slide off now?
Sure.
And we can, okay.
Yeah, if I need, I will ask you, okay?
Sure.
Yeah, sure.
So to start with this podcast, now we have a time restriction. We will, as I have announced already, we'll try to keep it at 9 o'clock, and requesting all the viewers to ask quick questions if you have for Professor Nilanjana. So it all started with a Big Bang. I mean to say the universe is expanding, but at one point of time, the universe was a very tiny, small dot, and all the energy was at a very small point. And then there was a Big Bang and the universe started. So if I take, Doctor, that the first few seconds after the Big Bang, so what role actually the particles play in shaping the early universe during the first few seconds after the Big Bang?
Okay, so I'd request you to share the slide again. So that would help me to, so just one slide I need. Okay, so yeah, this is a very familiar slide. You all know about this popular diagram of how our universe evolved, starting from the Big Bang. So after the Big Bang, we had a rapidly exponential expansion of the universe, which is termed as inflation. And then after that, what we had here is, here you can see in the first slice, we have all the particles and the radiations there. So these all the particles so far that we know of that consist of the standard model of particle physics were there, present there. And if we, it is also possible maybe the dark matter that we don't know of, the particles are still there, it was there. So after that, what happened, this becomes a quark gluon plasma. And after that, slowly you can see here the quarks start and gluons, they starts to recombine, and slowly the nucleosynthesis process begin, the helium nucleus form, then the lithium, and it goes on in the periodic table. And slowly what is happening here, the more heavier elements are forming, but as you can see, the electrons are still free, the neutrons are free particles, and also the photons are free. So until it is like 3 times 10 to the power 3 years after has passed after the Big Bang, what happened here is that the nucleus, they takes the electron in it, and then it forms the atom. And once all the electrons are absorbed inside the atoms, then only the photon becomes free, because there are no more electrons available for the photon to go through a scattering process. And that's the first picture of the early universe that we see today in the, and we all know the name, that is called the cosmic microwave background radiation. That's the first visible picture of our universe, and those are photons are actually reaching us. So after that, we still have the neutrinos left, and all the other particles has formed the elements. And that's why we still have all the neutrinos coming out, coming to us from all directions. And slowly as the universe evolved, the galaxies formed, the structure formed, and then we have our universe here as we stand. We only have us, we have the galaxies, our space-time curvature is mostly flat that we know of, and we have the free neutrons and only the photons. So this is how in a very crude manner, I have tried to explain it, what happened after the Big Bang. But what I want to point out here is this, the first slice. So in this first slice, we have all the particles that we know of. Like, we know about the standard model of particle physics, but we don't observe these particles roaming around in our house or somewhere else. We only observe the electrons and neutrons mostly. So in order to produce these particles, what we need are called the colliders. And as you can see, this time slice, 10 to the power minus 10 seconds, this corresponds to 100 GeV. So where the collider operates are at this energy, or the energy much higher than that. So that is the need for the colliders. In order to create the situation of early universe, we need the colliders. I mean, if there is another particle or any extra very interesting physics is happening, how can we probe that directly? That's why it's the accelerators come into the picture. And so far we know, we have discovered all the particles in standard model of particle physics. Yeah.
Yeah, thank you very much. I'm putting the slide up. Jude, let me know whenever you need it. We already have one question coming from Manojit, and he's asking, what are the cutting edge problem in cosmology people works on?
Oh, that's a nice question, Manojit. So in cosmology, nowadays what has happened is that cosmology and particle physics are going hand in hand. So whatever are the problems in cosmology, there are basically two parts. One is the GR, the general theory of relativity. There is a lot of unanswered questions there. The other questions, that is, like, people talk about this inflation. Now, is it the only theory that is the possible, or there are theories like bounds or something else? Now we still do not know which one is the correct one. Everything is tries to explain the observations. So that is one. Then another problem that currently cosmology does have is that we have observed the gravitational waves that we all know of. Now there are sources of primordial gravitational waves. Primordial means that is not coming from the merger of two black holes, that's what I say. So what can be the sources of these primordial gravitational waves and how to detect them, that we do not know. Then we know that our universe is, the driving force of our today's universe is the dark energy. Now, when we talk about the dark energy, how to model the dark energy, there are some discrepancies in the value of the Hubble constant measurement as well. So these are kind of the problems that the cosmologists are working on currently. So yeah, with the interface of particle physics as well.
Yeah, I'm so sorry. I'm so sorry. There was a
Oh,
problem with the camera.
oh no
Okay.
issue. Yes.
Okay. So we already got few questions coming up. So I will just quickly take them up.
Sure.
Manojit is again asking, what is special about neutrino in the area of cosmology and why it is so important to predict the edge of the universe?
Yeah, so neutrinos, again, when I was showing you the slide, you saw that there are only three particles available, right? So here, the particles that are crossing us all the time are these solar neutrinos, or the neutrinos can be from the early universe as well. And so that's why it becomes, so these are the particles that are available to us. Firstly speaking, like photons and the neutrinos that we can get from the early universe. Then secondly, the neutrinos, if you think about, it's very important in a theoretical aspect, because when you do the calculations in cosmology, you have to give at the early universe how many number of particles or degrees of freedom you can fit in the equations. And there the neutrinos, actually you can fit a little more than three. That is still a puzzle. It's exactly three, but it's little more than three. So the neutrinos are very important, and we know that the neutrinos exist also. And there are some other things I can think of. Yeah, so there is something called primordial black holes. So, or just think of a black hole when it evaporates via Hawking radiation, it gives you the flux of neutrinos also. So in general, if you see a very, very, very highly energetic neutrinos in the direct detection or indirect detection experiments, you can say that there might be this maybe is coming from a black hole when it is in a stage where it is evaporating. So yeah, that's why I think the neutrinos are most
Very
important.
important. Yeah. I would request also Manojit to, if you're really interested to know about neutrino, there's a very first podcast was on neutrino. That was with, that was with, I forgot the name, Alicia Castro and
Hmm.
Jessica Turner. Yeah. Jessica Turner from
Oh,
Durham University. She is a specialist on neutrino and early universe. So you can go back to my podcast list. It was in September 2023, which was on the importance of neutrinos in cosmology. So Manojit, you can go, and that is an exclusive podcast on neutrinos. You can watch it. Thank you, Professor. Oh, we have a question. Can we take it? I don't know. It might be
sure,
a little
sure,
bit
no issue.
trickier. Yeah. So what he
Let's
is
see.
asking is Stephen Hawking's work are one to be admired, but the Hawking radiation says that information is erased from the universe once after the evaporation. What about this? Was he wrong? The work of his life?
Oh, but the Hawking radiation says that information is erased from the universe. Uh, okay, so don't understand the question fully, but maybe what you were trying to say is that, see, when suppose you are talking about the Hawking radiation, that means you are talking about mostly a black hole in general. So in black hole, we know that whenever there's something, some information or light goes there, there is no escape to that, so no information can come to us. But Hawking, actually what he proved it that is that near the event horizon, the space-time curvature is, space-time is so curved that it allows it to evaporate. In a way, it is analogous to Kashmir effect, if you know what it is in quantum theory. So what he did is that he solved the field theory that in a curved space-time, and he showed that how the particle can be evaporated from the event horizon of the black holes. So when the particles are creating, it's like when you read quantum mechanics, you have these operators like creation and annihilation operators, something like that. So they are just creating uh, out from the vacuum. You can create the particle. So when a particle is coming out from the Hawking radiation, you can think that they don't have any information of how the black hole was formed, what are the characteristics of the black hole. It only has certain energy of the particle, that it has certain energy that is related to the temperature of the black hole, or the, in a way it is. So, and other than that, it doesn't have any other information. So I hope that answered your question. So it doesn't know anything about the black hole itself. So it's just
Absolutely.
emitting certain radiations. Yes.
Absolutely. Okay. Vitastro is asking, is there any universal rest frame? I also don't understand this question. Maybe
Okay.
Professor.
See, the rest frame is always relative, right? So if you are making, suppose I want to answer it in a different way. Suppose you are making you were doing an experiment, right? What is your rest frame? Where, so you can make it like that, where the observer is sitting, or if he or she is sitting on the experiment, then that is the rest frame. And from where he is observing the experiment, he will get one result. And if he is observing from the next door, that is that experiment where it is happening, that is not a rest frame to the observer. So he will observe something else. So that is not a rest frame. So it all depends on how you are looking at it. So in my opinion, there is no universal rest frame. It's all relative.
Thank you for answering, Professor. We have got a very interesting question coming from Debolina. She was talking to me. She's a master. She's doing her master's from Ramakrishna Mission. But before that,
Okay.
Raghav has got a very philosophical and interesting question. Maybe, Professor, you would be willing to understand. Ma'am, in the beginning of the universe, the time exists or not?
Oh, that's a debatable question, actually. So, in the Big Bang theory, what we say is that that is the time t equals to 0. But there are many believers that they say that our universe was just like that, like you and I are talking, something like that, and then it collapsed and went to a point of singularity, and then it started expanding again. So there are theories like that. So in our clock, or what we measure as a time, when we say that our universe was created 14 billion years ago, that is the t0, t equals to 0 second, we believe that is the Big Bang. Now what is exactly happening around the Big Bang, what is the Big Bang singularity, is it a removable or not, for that you have to learn a lot of general theory of relativity. And also there are people who work in quantum gravity. They try to address this situation, like what exactly has happened around that point of singularity, so that the universe started expanding again. So yeah, that's a very nice question.
Yeah, thank you. Thank you, Professor. Okay, now Debolina is asking, can you give an overview about particle physics? What does it
Oh,
actually have in the core concept? As we basically know, it deals with elementary particles. Is there anything more about it? I think you are
sure.
the absolutely the right
Oh,
person to
that
answer.
will be a 1 hour presentation maybe, but yeah, I will try to make it short. Thank you, Debolina, for the question. Can I share the slides? Yeah. So yeah, some of the I need some of. So Devalina, you the most of the stand you are in master, so you might have heard about these four forces of nature. So whatever is there in the standard model is basically weak force, electromagnetic force, and strong force. If you know all these three forces, you basically know the standard model of particle physics. Now gravity is effective in a very large scale, so its strength is very, very, very small. As you can see, it's 10 to the power minus 38 compared to the strong interaction which binds the quarks and gluons together. So gravity doesn't affect. So in standard model of particle physics doesn't consider the gravity in it, but it has this weak electromagnetic and strong field in it. As you were saying that these are the all particles that you have heard of maybe. So that is these are the quarks, and these are the green ones are the leptons, the orange ones are the quarks, and these are the baryonic matter, as far to say. And then what you have in the blue are the force mediators, like these are the photons, these are the gauge bosons, gluons, W and Z bosons, and in the center you have something called a very interesting particle that is called the Higgs boson. So to answer your question, let me just show you, like this. Apart from these particles, there is something very interesting going on. I don't know if I have the slide or not. No, I don't have. So there is something called spontaneous symmetry breaking. Actually, I don't have the slides, sorry. Okay, so there is something called the spontaneous symmetry breaking in the standard model, by which this Higgs gets its mass, and it gives the elementary particles the masses. So there are by the mathematical construction of the standard model, you cannot write the mass term for the quarks or the leptons. It's the interaction of the Higgs gives them the masses. So that in a sense is a very wonderful theory. Like without the Higgs, the standard model doesn't exist. So that is kind of, you can think of, it's a new thing that is there in the standard model, apart from all the particles only.
Absolutely. So, Debolina, just what professor is trying to tell, that this is a huge area which can be talked. That overview of particle physics cannot be done in 1 hour, 2 hours. Maybe it would require a semester.
You need to learn the group theory as well.
Absolutely, absolutely. Before coming to Raghav's question, Professor, can you suggest for the beginner levels, if they want to understand particle physics and its relation a little bit with cosmology, what are the name of the books that you would suggest, and what is the mathematical knowledge that one should have if they want to learn particle physics?
Okay, so book that has cosmology and particle physics both, I don't know of. As far as my knowledge is, I don't know of any such books. But the thing is, the particle physics community and the cosmology community, they grow separately. And then now the today's need is that they should go hand in hand. So now in order to learn particle physics, see, if you are in master students or just have done your masters, you are working, you want to know a little bit about the particle physics, your first basic is that you have to know the relativistic quantum mechanics, you have to know the Lie algebra, you have to know the group theory, like basic SO2, SU2, SU3, these groups, and the generators, the how to do the Lie algebra, how to perform that. So, and when you that is one level of understanding the particle physics. For that, you can read the book by Halzen Martin. So when I was a master student, I read that only at the beginning. Now when you are going in an advanced stage, you should read the quantum field theory, because if we read quantum field theory, then only you will know why you are drawing those Feynman diagrams in particle physics. So that is again very important, a very basic book. There are a lot of books written by the stalwarts in the whole world, but I started with Pal Lahiri. So that is the first book, very small book, but if you read that,
Professor told, this is Quarks and Leptons by Francis Halzen and Alan D. Martin.
Yes, correct. Yeah.
Yeah, okay, thank you. So we will come to the next question. Now, Raghav is asking, ma'am, please tell us about Hawley-Nardekar theory.
I don't know what is that.
Yeah, I think this is
I am not a person. So
general relativity. Yeah,
I've heard about this name, but I don't know about this theory or details of it. Sorry.
Yeah, okay.
You might invite some cosmologist and write down the question to ask him.
No problem. Okay, we have got a question that's, I'm so sorry. Yeah, Scientific Irfan is asking, the vacuum energy density of quantum fields contribute to the dark energy, but I want to know how does Higgs field has anything to do with because it has non-zero vacuum expectation value?
Okay, no, the Higgs cannot do it. So the dark energy, quantum fields contributes, vacuum energy density of quantum fields contributes to dark energy. Yes, but I want to know how. Okay, so the idea of dark energy is explained in in a lot of ways, but basically it's either by the cosmological constant lambda, or it is explained by a scalar, that is the quintessence model. Now it has the demand is of the dark energy, because we know about the density, we know the flatness of our present universe, so it restricts the quintessence to have a very 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 small mass. So no, it cannot be Higgs, that's why. So what happens is that the quintessence rolls over a potential, very very flat potential, and its excitations is there, and that is actually a model that tells you how the like why the universe is expanding today, or what is the energy source of its expansion. So that is the dark energy.
Okay, thank you. Professor, my next question would be that when we talk about the idea of inflation, now
Mhm.
what is the particle physics, or what are the theories? How do we actually understand inflation through particle physics? If you can explain us.
Okay, so the theory of inflation is that it has to go through a rapid exponential expansion, and you have a valley kind of a potential where the model is such that scalar field it rolls over uh, the potential, and at the when it reaches its end, there the inflation should stop, and the universe is inflated enough, and then it's the normal evolution starts. Now where the connection is that when you talk about the scalar, the question comes, can it be Higgs? Or if it is a Higgs, what are the consequences? And if it is not Higgs, what are the other scalars can contribute? And there you have to take the beyond something what is called the beyond standard model theory. So there are many unanswered questions in physics or in the observations also that standard model cannot explain. For that we have to go to something beyond. That means sometime that the new theories are going to give you some extra particles, maybe suppose a second Higgs kind of a thing. So is this the second Higgs is driving the inflation or not? Or maybe there are two Higgs particles or two scalar particles that they are driving the inflation. That is one point where particle physics comes in. And the other point comes in like this is a cold inflation scenario I am talking about. So what happens in inflation, that in cold inflation, when the universe exponentially expands like that, its temperature drops. Now the temperature cannot drop because the other evolution processes, then it will not go through it. So in order to reheat the universe, there is a mechanism called the reheating. It's a very popular scenario studied by a lot of people, where the inflaton now decays to different particles, and it populates the universe. So that reheating mechanism, how it decays, the inflaton or the scalar field decays to the other particles, be it standard model particles or some non-standard particles, and how to model the expansion after inflation, where this is the place where you need the particle physics and cosmology to go hand in hand. So
Okay,
this is a very crude way to tell you that.
tell you, yeah, yeah.
So
So
yeah.
Raghav is telling, thank you, ma'am, for giving answer to my
Okay,
question.
thank you, Rahul.
Yeah. My question to you, Professor, is that this is just an idea. I mean to say, whenever we are talking of a very complex model, either we are talking of particle physics, fields, or
Mhm.
cosmology,
Mm.
in general,
Mm.
what we try to do is that we think of a model, for example, flat space time, but the curvature, density, etc., a little bit less, so that the calculations are a little bit easier. Once we get a model, then we extrapolate that model to further complexities. Now, in case of relativity, I mean, I'm to say, for example, special relativity, etc., we assume a flat space-time, Minkowski
Mhm.
space-time, where things are
Yeah.
easier. So my question is that in particle physics or in cosmology, do you also have a similar kind of assumption of a easier flat space time? I mean to say, in particle physics, as we understand, these are very little particles. So do we
Mm.
have a space time where it can be very difficult curvature, and we assume a flat space-time, and from there we move into complex things. How things actually happen in particle physics?
Okay, so that's what I was telling you. The GR, the general theory of relativity, and the particle physics, the evolution of these two subjects happened separately. So when you think about particle physics, what do we have to do? We have to do the quantum field theory in order to get the Feynman diagrams, in order to know what particles are coming in, annihilating, and giving me what are the masses of the particles, and all these calculations. When we do, and we do write the metric, we do it in the flat space time. So all the particle physics books that you will find, mostly these are assumption is that the space time is flat. Now that is for everything, like when you talk about the supersymmetry or the suppose extra dimensions and all, the space time is flat. So that is the gravity is not interfering with anything. I mean, I'm not talking about the string theory, that is a different thing. So, and the thing is that the only thing, as I was talking about the black holes, when we talk about the places where the space-time curvature is very, very, very strong, like at the time of Big Bang, or at the time of Hawking evaporation, there, if we want to look for a particle and if we want to model some particle physics phenomena, we have to do the whole quantum field theory in a curved space-time, and that changes a lot of things. Like, as you can see, if it's a flat space-time to a curved space-time, you need to do a very, very complex mathematics, right?
Right,
And that's what
right.
actually was the work by Stephen Hawking. So in basic particle physics, the assumption is the space-time is flat. Yeah.
So also in quantum field theory, when we are learning, we assume it is a flat
Yes.
space-time, and then we,
Yes.
okay, fine, got
Yes.
it. Okay, very two interesting questions coming up. The first one is by Muhammad Hamza. Now he's asking, universe is expanding. What is expansion in reality?
What is expanding in reality? So the space time, so it's, you can think of space time as a fabric which is expanding. So it was a fabric. Now if you have a fabric, maybe uh, a leather or something like that, I don't know, and if you just stretch it, the space and time both are stretching. So this thing is expanding. Like whatever was the constituents, the energy, total energy, everything is conserved inside, but it's the fabric is expanding. You can think of it in a three-dimensional way, actually. So yeah.
Thank you very much. Okay, now comes a very interesting question from Brishnu Prasad, a very old subscriber of my channel. Ma'am, how to build a career in cosmology?
Okay, so are you a master student or a PhD student already? I don't know, but I guess you are
I think he
masters.
is a master's. Yeah, yeah, he is a
Yeah,
master's student.
okay. So it's good to know that you are interested in cosmology. So basically, you have to learn, if you're interested in solely cosmology, and you have to learn the spatial theory of relativity first. Then you have to know the quantum mechanics. Like quantum mechanics is kind of the core subject of anything. If you want to go even the GR, or if you want to go do particle physics and learn quantum field theory, quantum mechanics is something you should know. And then, okay, you are a BSc student, so quantum mechanics you should know. And then you should know about this electricity and magnetism. You have to you have to learn. Then only you will understand what is the importance of the spatial theory of relativity. And after that you will learn what is the general theory of relativity. And basically you have to master the general theory of relativity if you are interested solely in cosmology. But it again depends on different fields, like people who works in quintessence model or the dark energy models. You have to know a little bit of field theory for that as well. So these are the basic courses, and in India all the universities have these course structures that you
I
can
think
take forward. And, yeah.
SGT University also has something specialized to cosmology if somebody
Yes,
wants.
yes. Yeah, so in our university, our master's courses are designed in such a way that in the last semester, if you want to take a specialization in the cosmology or particle physics, you can do that in CCSP. We are a center, but we work hand in hand with the physics department as well. So we teach them like the basic BSc and MSc courses, and they can do the specialization in cosmology, astrophysics, and particle physics in our center. So yeah, we do have that option for the master student.
Okay. We have a question. I cannot pronounce his name. Anyway, will time reverse during the universe big crunch?
No. So, so this is actually kind of a hypothesis. So the time will not reverse, but everything will go reverse. So time will be expanding. So how you draw it is that it's going, the universe is expanding, 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 and then it is again collapsing. So everything will collapse. As I was discussing, it's space time is a fabric. The fabric is collapsing, so the time is not collapsing. So yeah, so that's what I think you asked.
Okay, thank you. Vishnu Prasad is telling thank you, ma'am. Okay, there is somebody, I think, Tuhin, glad to work there in CCSP. Maybe a student
Okay,
of yours.
yeah, to him I don't remember. Okay, maybe.
Okay, yeah. Okay, so we have few minutes more. Professor, my next question would be that, uh, for example, when we are talking about dark matter, especially when we are talking of dark matter detection. I was always thinking that if you talk of the LHC, right, the Large
Hmm.
Hadron Collider, so LHC actually does a lot of experimentation in terms of particle
Yes,
physics. Dr. Sudeshna of Fermilab came in a podcast. She explained what Fermilab does. So my question is
she's
that
my batchmate from
Dr.
Bethune
Sudeshna,
College. Yes.
oh, Dr. Sudeshna Ganguly.
Yeah.
Okay, yeah,
Yes.
okay,
Yes.
great. Okay, good to listen. Yeah, she was also came in a podcast
Mhm.
on particle physics, especially
Oh, okay.
last year. Okay, yeah, okay,
Hmm.
great, great to know. Okay, fine. Oh, see, she's from Bethune. Okay, same then.
Yes, she's from Bethune. Yes.
Okay. So what I was asking is that this collider experiments, which happens
Hmm.
in LHC, uh, how do they contribute to the search of dark matters? I mean to say, what are the challenges? Do we actually do something in LHC to detect dark matter, or we are just
Hmm.
experimenting on the particle level?
Okay. So can I share the slides again? Okay, I just want to show one thing. Yeah. So yeah. So see, there are a lot of debates. Like dark matter can be a particle, or it can be something else also. Like the primordial black holes can be a dark matter candidate as well. But I'm not going into the debate. But if it does, it is believed from the like dawn of supersymmetry actually, that it's called the WIMP miracle, and that tells us that if that there are supersymmetric particles, if they are the dark matter candidates, then there is a way to detect them. So what happens in the collider is that you can see this diagram on the right, that here this, yeah, this two red yeah things. So this is kind of a collision point. Suppose what happens in LHC collider is that there are two proton beams, they come and collide, and when they collide means the particles are annihilating, and then they are creating a lot of particles. As I said, here we are creating an early universe phenomena where we can create all the particles. Like we can create Higgs even though we don't observe Higgs. We can create the dark matter also if it exists in nature. So if it's a dark matter, then it doesn't talk to you via the electromagnetic waves, because it that's why it is dark. It doesn't interact with the photons. Now then how will you know? So what they calculate is that on the vertex, if there is a mismatch in the energy calculation or not, like the energy of the incoming particle you know the energy or momenta of the outgoing particle. So if there is a mismatch, then we can say that it's a dark matter candidate. But there is a problem there. The neutrinos also behave in a similar manner. So they have to model how does the missing energy, that is the term that has been coined for these detections, how does the missing energy looks like for the neutrinos, and if it's a dark matter particle it will look something different. So these missing energy signals the LHC detectors are looking for. If they can see something, some signal like that, we can say that it might be a possible dark matter candidate was. It is possible that a dark matter candidate was produced during the collisions. So that's how LHC mostly works to detect the dark matter particles. There are several ways, but that is the most common
Okay.
yeah,
Okay.
process. Yes.
Okay. So that means, I mean to say, there should be a kind of a signal which will tell
Yes.
a kind of an indication.
Exactly.
Okay. Okay. Good.
Exactly. And
We
a
have
lot of people actually work on how to model those signals, including myself and my other
oh,
collaborators. We model how does the signal looks, not only for the dark matter. Suppose we work in a supersymmetry or some other models, how the model signal will look different from any standard model signature. And that's what we do in our research work, so that when the experiments are going on, the experimentalist can look for those signals actually uh, in real time experiments.
okay. A few quick questions because we are already
Sure.
approaching 9 o'clock. So, first is that I think this is quite a pretty simple question. Sun is rotating around the Milky Way, or the universe is not stationary. How do we say this? Because we cannot go to see these things. What is the experimental evidence to see those things?
Okay,
I think
sun
the
is
space.
rotating around the Milky Way. Around
No,
the Milky Way.
I
Okay.
think, Professor, what Hamza is trying to tell,
Ah,
that the entire rotation of the
mm.
planets around the stars, etc., we cannot see that. What is the way, or what are the experiments which can take a photograph or something which
Mm.
can show that yes, it is actually
Oh,
moving? And
okay. Okay, so for the universe, it's like how do we know that our universe is expanding? We know it from the Hubble's law, right? So what happened is that Hubble observed that some galaxy, when it is he measured the speed of how much the galaxy is moving away from the earth. So this, and that is speed is proportional to the distance of the galaxy from the earth, and also some constant, that is the Hubble constant. And later it has been seen that anything, if you measure, you will see that everything is moving away from us, like away from earth, if you are doing the measurement. So that is the first proof, actually was much before the cosmic microwave background actually, I think so. So that give you the idea of that expanding universe. After that, when CMB came, we know that is Big Bang was one of the theory that we have, and that is we have the expanding universe. But this is simply from Hubble's law. You can say that our universe is expanding.
right. Okay. SSJ is asking, is space-time really made of anything, or is it just a hypothetical concept to describe gravity?
So space is made out of matter and radiation, and you have the time. Time is kind of an invisible to us. So when we coin these terms like space time is stretching, think about uh, a sheet or something like that. It's all actually to like to visualize it. So suppose like when you do this something called the co-moving coordinates, you draw the grades, and then the distance between the two observer is fixed even though the space time is expanding, all these things. So there is nothing such called a time you cannot see, right? But the space means it's just matter and radiation, and matter means both visible and dark both, and dark energy is also present there, but we still don't know how to like know
Absolutely.
that the
Yeah.
evidence of
Yeah.
the dark energy yet.
Okay, Devolin has got a question, although it is a little bit out of the topic, but I'm still taking it. Ma'am,
Okay.
we do know that particle physics deals with elementary particles. Then what about the string theory concept, where every particle
Hmm.
is considered as strings?
Okay. So first of all, I don't know about the string theories, but see, the thing is, I actually didn't tell you about. I mean, I didn't tell you like the standard model of particle physics. it has a lot of drawbacks actually as a theory. So as a theorist, when some theorist is trying to tell you a theory, he or she tries to be perfect. He wants to cook up something which is perfect from every angle. The standard model of theory, it's kind of a phenomenological theory. So things, we try to put it into it to making a working model. So there are a lot of things that are ad hoc in the standard model. So that's why people work with alternative scenarios, like other theories, like supersymmetry is one example. Now, string theory is a totally different theory that gives a lot of predictions for the particle physics as well that the standard model cannot explain. This is one way to look at it, I think. And string theory has some other like things to do, predict
Candidate
also.
theories, etc. Yeah.
Yes.
I will come to two very interesting questions. I'm rushing up. I may just take 2 minutes
No,
of
it's
your
okay.
time.
Fine, fine, fine.
Okay. I just want you to explain in a very simple language when we talk of spontaneous symmetry breaking. If you can
Ah,
just tell us that what actually is and why it is called
okay.
spontaneous. I mean to say,
Ah,
spontaneous means it comes automatically. Is it not mechanical?
sure.
So if you can just let
Yes,
us know
yes.
what is that.
Yeah, yeah. So I think I have a slide on that. Might be. I don't remember it. No. No, yes. No, I think do I? No, I don't have the slide. Okay. So think of it in this way. So it can stop my slides. Yeah, so think of it in this way. So when you have heard about the paramagnetic and ferromagnetic substance, right? So when you have a ferromagnetic substance, that means you, so when you have a paramagnetic substance, suppose your magnetization is it's random, it's kind of a zero in some scenarios also, right? Because one small, if you think of it, consists of small magnetic dipoles. One is directing in this direction, another one is this, and the net magnetization is zero. But if you reach a certain temperature, you know that there is a phase transition and the paramagnetic substance can become a ferromagnetic substance. When that happens, if this is happens mostly at a certain temperature, and then all the small magnets you can think of, they are aligned, and so they are aligned in one direction, and the net magnetization is not zero. So that is when the magnet, small magnets were has the like a orientation in different angles. That was very spontaneous. You don't know how to predict the directions of each magnets. But when you have the net magnetization, all the magnets are aligned, and you have a m not equals to zero, then that symmetry is spontaneously broken. That is an example of the spontaneous symmetry breaking in our world actually. And that's the similar kind of thing happens to the Higgs potential in standard model. The symmetry is broken at a certain temperature. And now if you think of a potential like that, the minima is at zero, right? Now when you have break the symmetry and make it a Mexican hat kind of a potential, now that the zero where the particle is, it has to choose which way to go. Like either it will choose go to left or it will go to right. And if it once it chooses one of the minima of the potential, it chooses a certain direction. Like the ferromagnetic substance chooses one direction of magnetization, and that means the symmetry is broken. So that is one example of the spontaneous symmetry breaking, where the symmetry breaking is happening from inside the material. You are not doing anything. It's the property of the system.
Okay. So that means it is some kind, we can say, although it would be wrong, the least action principle. Whatever the path the particle will take itself, that it will take that own path. Spontaneous is something which is within the system. It will take what the system, the nature will decide. Something like that.
I don't know if I understand the analogy completely, but yeah, maybe. So the opposite or the other way around to break the symmetry is called the explicit symmetry breaking. So you add something by hand, you add a
Okay.
magnetization field by,
Yes.
and then the
Right.
symmetry is broken, or you do something. But that is not something. It's a like you are just maybe the tip. So there is something called order parameters, right?
Order
So
parameters,
these
right?
order parameters are controlling the symmetry breaking
Symmetry breaking.
phenomena. So
I
that's the
got it. Thank you.
spontaneous. Yeah.
You are an absolute great speaker who can draw very simple analogies to explain. Thank you.
Okay.
Okay,
Okay.
coming to
Thank you
few
so much.
last questions. Yeah,
Sure.
I have a great last question. Can the universe be viewed as a black hole? Try searching the radius and mass of the universe and use the Schwarzschild radius.
Try searching the radius and mass of universe. I mean, first question would be why it should be a black hole. Then we are
Yeah,
not talking actually. Our universe is a black hole. But yeah, there are a lot of evidence of black holes. They are there. That is for sure. And what is the next question? I don't get. Try.
I also could not understand. Try searching the radius and
Yeah.
mass. Okay,
So
we go to
maybe
the
he is asking that in an alternative scenario, if you have a massive black hole of our size of our universe, yeah, definitely you can take that mass into account. You know the size of our universe. You can calculate the Schwarzschild radius. Just need
yeah.
the mass actually to calculate.
Actually, yeah.
Yes.
Faisal Azmi is asking, do you have any favorite reference for a book which speaks of the contemporary development in cosmology with a great clarity and yet the minimal of mathematics?
I can't think of any book right now. Cosmology, right?
Or maybe, Professor,
Maybe
if
I
you,
can share with you
yeah,
later
you
on.
can share that
Yeah.
on LinkedIn onto my profile. I will just share it. Okay. Sardar Zaid is asking why most of the experiments for dark matter particles at the
Hmm.
GeV scale. However, it could be
Hmm.
at some lower energy scale.
Absolutely, absolutely. So, most of the experiments of dark matter it started as of from the WIMP miracle, as I was talking about. So, in supersymmetry, WIMP stands for weakly interacting massive particle. So, when this theory was proposed, that okay, in this theory we have a lot of massive particles in the GeV scale, and if they have certain small couplings with the ordinary matter, then there is a hope to see the dark matter in the direct detection experiment. So that is why it matches accidentally, or you can say that in supersymmetric scenarios. So that's called the WIMP miracle, and that's why the dark matter search began in that GeV scale. But still there is no observation of dark matter in the GeV scale. So that's why there are a lot of other experiments nowadays, which are like xenon, then ice cube is there, then lead zeppelin and the lz experiment. These experiments are looking for very 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 low mass dark matter, like axions can be dark matter also, right? Then the right handed neutrinos can be dark matter. So these alternative dark matter particles you can search for, or a scalar particle dark matter also below mev scale, and they have gone I think up to kev scale also. So there are dedicated experiments nowadays they are designing, and some of them have started taking the data
Yeah.
as well. So in the
I
KV scale as well, light dark matter.
Actions remind me just before your podcast, there was a professor of particle physics, Alessio Mastrodi from Italy, and he
Mhm.
actually talked a lot about actions.
Oh,
His specialization paper is on actions. Okay,
okay.
I'm rushing up just 2-3 minutes more, ma'am, because
Sure, no
there are
issues.
so
Yeah.
many
You
people
can
are
take 5 more minutes. Yes.
willing to
Yeah.
know. Okay, uh,
Sure.
Nirupankar Sharma is asking, okay, yeah. Before grand unified theory scale temperature,
Mm.
we go to quantum gravity. Is
Mm.
quantum fluctuation just added to the gravity in this framework?
Okay, so this is kind of again an eternal question. The theorists are still trying to write down a quantum theory of the gravity. That is actually the field of quantum gravity. So when we think of this Big Bang thing, the space time was heavily carved, and at that time there must have like there has to be some fluctuations should exist. Otherwise how are we getting all these energies that we have in the universe in the form of matter and radiation? So how to model that people are still working on. There are different in different levels, people have worked on quantum gravity actually, and this pioneer, the Thanu Padmanabhan, he has done some work in this direction as well, as far as I know. Yeah.
One's actually great lecturer. I
Mm.
have,
Yes, yes,
great
yes,
person. Yeah, absolutely.
yes.
Okay, one question which is a little bit broad, but if you can summarize, Professor. Hamza is
Mhm.
asking, ma'am, can you explain what is Higgs field and how it gives
Mm.
mass to other particles?
Okay, so the answer is there are two answers for it. One is the popular science answer that I can explain here, Rairam, and another answer is that for that I need a blackboard maybe. So to answer your question, so this thing I was talking about, the spontaneously broken symmetry. So Higgs particle, this is a scalar particle, and you can write down a potential for that. You know that from your Klein-Gordon equation also. So you can, when you write down the potential and you break the symmetry spontaneously, if you do the calculation, you can see that the Higgs gets the mass. And if you write down the Lagrangian, like expand the covariant derivative terms and do like write down everything, you will see the automatically the interaction with the standard model particles, of interaction of the standard model particles with the Higgs are coming in, and those beautiful mathematics will give you some terms that will be the mass term for the leptons, for the hadrons, for the Z bosons, and the uh, W bosons. So basically, all the masses, these are going to be proportional with something called the vacuum expectation value, or V, small v, which is proportional in a way to the Higgs mass. So that's why when we found the mass of the Higgs to be 125 GeV, we were thrilled and we knew for sure that the standard model is an 100% like confirmed theory, because 125 GeV Higgs can give you the masses of the electrons that we know of, that can give you the masses of the quarks that we know of.
Absolutely. Thank you. Last question to you,
Yes.
Professor. Uh, the role of future colliders, for example, the International Linear Collider,
Mhm.
the Muon Collider, what
Mhm.
is actually their targeting, and what actually the role that it plays in answering some of the cosmological questions that are not answered related to dark energy? What is the role of these future
Mhm.
collider experiments?
Okay, so to answer your questions, there are certain limitations of this Large Hadron Collider experiment. So again, when the experiments are being built on the demand of the physics actually, so when LSU was built, the aim was the supersymmetry was in the with a very hot theory at that time, and the aim was to look for the supersymmetric particles which are in GeV scale and to look for the Higgs boson as well. So the target, so that's why we have a PP collider that can reach very very high energy. It's currently operating around 14 TeV, tera electron volt. It can go up to 27 TeV in future, but there is a problem, like as protons are not fundamental particles, when you collide them you get a lot of quarks and gluons in the background, in the process. So you have to eliminate them to actually see the signal that you were looking for. That is called the optimization of the signal against the background. That is a problem. And in some cases, when we are not looking for a heavier particle or something, but we are looking to uh, do some precise measurements. In a sense, when you look for a lepton collider, which is the ILC International Collider, and then muon colliders, they are the lepton colliders. So you are colliding two electrons or two muons, which are the fundamental particles. So their background, what we call, like, you don't get a lot of chaos. So whatever you are going to measure, you can measure with great precision. Now
Okay.
coming back to your second part of the question, what it can tell us. So the one of the thing I can tell you, it is going to measure the coupling of the Higgs boson with other particles. So right now I told you, even though I told you the standard model is 100% tested theories, but the coupling measurements at Large Hadron Collider still shows some deviations. So, and there are a lot of the uncertainties are huge in some scenarios. So those precisions will increase a lot in the future lepton collider experiments, and it can shed light, it can look for at a dark matter at a different angle, it can give you some insights about baryogenesis as well, why there is an imbalance between the baryons and antibaryons. So these questions, I think the future linear colliders we can answer you better, because it has a totally different perspective now. It is going to look for very dedicated things where it is going to make some precise measurements mostly.
Thank you, Professor. And I would just request you, don't disconnect after we are done with the
Sure.
podcast. I will need 1 minute
Okay.
of your time. Any last minute message? I think you enjoyed the podcast because there were a lot of
Yes,
questions.
yes, of course. I enjoyed the podcast, and this is actually my first podcast. So thank you, Sona, for inviting me. And yeah, I would like to ask the students as well as you, when you visit India, you should visit our center as well. And anyone, if you are willing to visit us, you can follow us in our LinkedIn page, the CCSP. There is a handle in LinkedIn as well as in Facebook. And if you want to join our PhD program, you can go look at our website, look at the faculty profiles. One faculty has joined very recently in works in cosmology, but this is not updated yet. But yeah, we have 5 faculties. So, and come, you can just come and visit. Just write to us.
Okay, Raghav
Yes.
is telling, ma'am, I want to visit your center.
Yes. So you, I think you can share my email ID with them.
I will do.
Can
Yeah,
you?
I will
Yeah.
just share.
Yeah.
Just hold
Please
on. I will
write to us.
just, yeah. Can you just tell me, it is Nilanjana? If you can just repeat
Dot
once more.
Kumar. So it's
Dot Kumar,
nilanjana.kumar@gmail.com.
gmail.com. Okay. So for everybody, this is our professor's email ID, nilanjana.kumar. I'm just flashing on the screen. You can take a note. And I think, Professor, that the young people do have a lot of future in particle physics, isn't it? What
Yes,
do you think?
yes. And I would like to emphasize that the future is there in the interface of cosmology and particle physics. Um, Only so the chance of survival is more there if you do like work in the the juxtaposition of both the theory.
Absolutely. And I will tell you, Professor, I am a specialist on GR, but when
Okay.
I talk to the students, when I sit in the defense committee, seeing their presentation, right now, I should not say, people might be angry on me, but they are just like my children. So, quantum mechanics, I mean, just quantum field theory, cosmology, and
Mhm.
particle physics. If you talk of the real life applications, just what you told, that there is a huge amount of scope, because
Yes,
quantum
yes,
itself, 2025 is UNO has
yes.
declared this as a quantum year, quantum revolution
Mhm.
year. So we
Mhm.
are getting a lot of quantum supremacy, quantum cryptocurrency, the credit card verification, everything is actually done on the quantum level. The flash drive. So there is
Yeah, yeah, yeah. I have heard about. I don't know of it that much, but people are trying to detect the dark matter in Australia or somewhere. My student was telling me, and they're doing something in the quantum level. They're
quantum level. Yeah.
something, some
If
experiments they're trying to do.
Right.
I don't
In the
know which one.
industry overall, we have got a huge
Mhm.
application of quantum physics. In
Yes,
the
yes, of
industry, we
course.
also have, in cosmology, we have got particle physics and cosmology. So yes,
Mhm.
you are telling is that the chance of survival, GR is
Yes,
more fundamental, research based, and lot of complex mathematics, real complex exotic mathematics are there, although particle physics also have it. So just a note of thanks. Debolina is telling, thank you, teachers, for the nice session.
thank you, Devalina.
And Rudrasi is also saying thank you. So thank you, everybody, and wishing you all a very happy new year 2025. We will be concentrating more on quantum physics. And thank you, Professor
Mhm.
Nilanjana, because the
Thank you very
most
much.
important particle is at your home. And I think that this
Yes,
particle is more than Higgs boson. And
yeah.
I think he, isn't it? He
Yeah, yeah,
is
it's a he, and you cannot say which state he is in. It's
right.
a
So it is a quantum
excited state.
superposition. Yeah.
Yes, yes, you cannot say. Yes.
So for the viewers, just to give you a hint, we are talking of Professor Nilanjana's son. So he
Mhm.
is there. He is the most important particle in the universe, and he is beyond the standard model. So wish him
Yes.
also good luck, good health,
Thank
and
you,
may
Sonal.
he
Yeah, I
also
do.
follow the footsteps of you, becoming a cosmologist and a particle physicist. Life is World is also saying thank you. So thank you very much. And we
Thank
will
you.
see you soon next year, because this is
Sure,
a good
sure,
learning that we have done. So
sure, sure,
stay tuned, and we will just say goodbye.
sure.
Thank you very much.
Thank you.